we look at the regenerative cycle, so here we're going to have it go into the turbine. It goes into the turbine, state 2. I'll make the turbine a little bit longer. So it's going to go in at state 2. It'll expand to state 3, and some is extracted. So Y1 is equal to the fraction that's extracted. So I have 100% here of the steam of m dot s. Y1 is equal to the fraction extracted. So it could be 20%. So if this is 100%, perhaps Y1 is 20% or 0.2, and the rest, 1 minus Y1, expands through the turbine. So we're going to have this go to a direct contact heat exchanger. And so this is at state 3. It keeps expanding through the turbine and goes into a condenser. So it expands through the turbine to state 4, comes out at state 5, goes into a pump, comes out of the pump at state 6, and goes in here, comes out of here and goes into another pump, and that brings it back here. And so here we have 1 minus Y1. So if Y1, I don't want to write down 20%, because if I write it down, then what you're going to do is say Y1 is always 20%. So as an example, Y1 is 20%, then 1 minus Y1 is 80%. We're going to have different Y1s. We're going to see how that happens. And so it comes out of here at state 7, and here we are, it's here. And if I draw the TS diagram, state 2 expands to state 3. We have Y1 is condensed. So what's happening is the steam is condensed. So the steam comes in here and mixes with the water, and we'll see what the assumptions are about this. The rest over here at state 3 keeps expanding. 1 minus Y1 expands to state 4. So this is 1 minus Y1. And then we have, it condenses to state 5. We have, it goes to state 6. We have a pump. It goes to state 7. And then we have another pump. Bring it up to the steam generator pressure. So we make some assumptions about this cycle. All liquid leaving heat exchanger has an enthalpy equal to HF at the extraction pressure. So we have that. And what we also wanted, so this is one assumption. So we're making that assumption. So it means that H7 is equal to H sub F at P3. We also, when we designed this, so in the ideal design, this delta T and this delta T are equal. So the question is, where do you have this occur? Where do you have this pressure occur? You have this pressure occur such that these temperature differences, these delta T's are equal. So we want P extraction such that delta T's are equal. Now, we may not have them be perfectly equal, but that's our goal. And so now what we need to do is to find y1. So if I have 100% going from 2 to 3 and 1 minus y1 going from 3 to 4, let's find out what y1 is. And we can do a first law on the heat exchanger. And if I do that, En equals E out. So I have Y1 H3 coming in, and I have 1 minus Y1 at H6 coming in, and I have everything leaving at state 7. So I can solve for y1. y1 is equal to h7 minus h6 over h3 minus h6. One of the nice things about this extraction or regeneration is that it's inherently stable. So what happens is I'll always have the necessary steam flowing. So I don't have to have a control valve on here. The extraction always works thermodynamically. If this is cold water, then more steam is going to come because the steam will condense faster, drop the pressure, and I'll have more steam coming. If the condenser goes into warm water, and this water temperature rises, then this is warmer and less steam flows. So I didn't mention that in part of my background, I was in the merchant marine and I operated steam power plants like this that were on the ships. So I have sort of an operational perspective as well as a design perspective for steam power plants. What I'd like to look at now is example 15.4. It's on page 552. And this is and I'll use the numbers there and you can see them, but I'll recover them. So first you make a sketch of the system, you make your TS diagram, then you're going to find all the enthalpies. And so our method is sketch, TS, find enthalpies, then do your first law analysis. And so we have that P2 is equal to 10 MPa. T2 is equal to 550 degrees Celsius. P3 is equal to 1,000 kPa. And P4 is equal to 10 kPa. So these are all values that we can look up in the steam tables in the back of the text. So H2 is equal to 3501.9. S2 is equal to 6.7549. P3 is equal to 1,000 kPa. S3 is equal to S2. And I can look up H3 is equal to 2856.9. So I can do that. And now, so in the text we see this is still superheated. And now when we go to state 4, it'll be in the mixture region. I'll have to find the quality, etc. And the text does that so you can see that. And so then I have for P4 is equal to 10 kPa. S4 is equal to S2. And so we have that H4 is equal to 2139.9 kilojoules per kilogram. H5 is equal to H sub F is equal to 191.8. H6 is equal to H5 plus V5 delta P. So that's equal to 192.8. H7 is equal to H sub F at P3. So that's equal to 762.5. So this gives me the enthalpy that's leaving here. H1 is equal to H7 plus V7 delta P is equal to 772.6. So the first thing we do is go all around the cycle and find the enthalpies. Now we're going to find Y1, and we'll eventually have more fractions. So this is the first one, then we're going to have multiple, another extraction, etc. But that's for the future. So now we find Y1. Y1 is equal to H7 minus H6 over H3 minus H6. So that's equal to 0.2176. So 21.76, nearly 22% of the steam is extracted, leaving 1 minus Y1, about 80, whatever I said, 78% going through here. And so now what we want to do is find the turbine work. And so when I look at the TS diagram, so part of what I'd like you to be able to do is that I can see that the turbine work is the isentropic enthalpy drop here. And so it's H2 minus H3. I lose Y1. The remainder, 1 minus Y1, expands between here. So I have 1 minus Y1 expanding here. And so I can look at the TS diagram. So we drew this, we draw that, we find the enthalpies. Then I can look at this and just look and see what the turbine work is. So the turbine work, I've got to erase this, but you have these numbers anyway. WT is equal to 100%, 1, expanding between H2 minus H3 plus 1 minus Y1, expanding between H3 and H4. So now I substitute in those values. 3501.9 minus 2856.9 plus 0.7824 times 2856.9 minus 2139.9. And so we have that WT is equal to 1206.0 kilojoules per kilogram. So I can find the turbine work, and then we go around and find the other energy terms as well. The pump work, so in this case, there are two pumps, so I have to find the pump work here and the pump work here. So WP1 is equal to 1 minus Y1 times H6 minus H5 is equal to 0.7824 times H6, 192.8 minus 191.8. So I have WP1 is equal to 0.78. And it's a pump work, so it's minus. I wrote it, I find it easier to write these things as positive numbers and remember the pump work is negative. You can look in the text and they did it so that it came out minus. And then WP2 is equal to 100%. So all the fluid goes there times H1 minus H7. And so that's equal to 10.1. Again, it's a minus. And WP total is WP1 plus WP2 is equal to 10.88. And W net is equal to 1206 minus 10.9 is equal to 1195.1. And then I can find the Qn, H2 minus H1, and then the efficiency. 3501.9 minus 772.6. Qn is equal to 2729.3. And the thermal efficiency is equal to W net over Qn is equal to 1195.1 minus 2729.3 is equal to 0.438. And so in example 15.3, which I didn't go through here, they took the example in 15.3 and they compared it where I didn't have regeneration to regeneration. So in example 15.3, which you I know have looked at, for example 15.3, W net decreased 11.6%. Why? The work went down because I removed some of the steam. I didn't get as much work out of this of the steam entering. It went down 11.6%. But Qin went down 17.3%. So when I look at the efficiency, this went down, but Qin went down faster, so the thermal efficiency went up 6.8%. So that's what regeneration does. It provides that. Now for homework, look at 1519, 1524, 1527, and 1528. What happens on ships, on naval ships, is that they're designed for efficiency when they're doing general cruising. But if you don't care about efficiency, what you do is you close this valve, you have all the steam go through there, so you have much higher power coming out. So in times where you need more speed, you may say, I don't give a darn about the efficiency, what I care is getting more speed, so I'll close off the extraction and have all the power go to the turbine.